My name is Ellen Ramirez, and I am thrilled more than I can describe to be your opening presenter for day 2 at the 2020 EAS. Thank you to L3 Harris for the opportunity to speak about my work in NOAA. I am a supervisory physical scientist in the NOAA Satellite Analysis Branch, which is on the civilian side of federal government, and I have worked in that unit for the past 10 years. Prior to that, I was in graduate school at the University of Utah, studying atmospheric science with an emphasis on remote sensing in the tropics. Specifically, I was using a 10-year satellite data record to look for indicators for tropical cyclogenesis. So after that work, I came to NOAA, and I really became enamored with the potential of what satellite data and its derived information had to offer. So I'm very excited to be here speaking to you this morning. And with that, I will share my screen. Okay, excellent. So the technical portion of this talk will be advancing satellite-based detection of marine debris. But first, let's talk geospatial vision for the next decade. What an amazingly simple yet powerful theme. I put a lot of consideration into the content of this narrative because when you think about it, time is the utmost non-renewable resource. So what you do with it and how you plan to spend your time, it truly matters. In order to set aims and goals and objective and to lay those out over 10 years, it requires a hard review of the past decade and a critical assessment of where you are in the present and revisiting lessons learned, and then letting that information be a guide to formulate a truly tangible vision for the next 10 years. So 2020, it hasn't done us many favors so far. A lot of us, we were already facing deadlines and complex challenges in the realm of data acquisition and analytics. And then the pandemic hit. So ready or not, it forced us to rework how we communicate. Today, I'm speaking to you from my home office in Gaithersburg, Maryland. It also forced us to re-examine our standard operating procedures and rethink how we can innovate new techniques to continue to meet today's and tomorrow's informational needs, but also not losing sight of the long-term goals. The start to this decade has demanded that we take stock of our resources and our operational capabilities and capitalize on the strengths and continue to move forward. So the technical highlight of this talk, as I mentioned, will be to spotlight one such way that NOAA continues to move forward in the realm of geospatial analysis. And it happens to be addressing a burgeoning environmental crisis, marine plastics. While this project is emergent and the results are preliminary but encouraging, one of the reasons that I'm inclined to talk with you about it today is because we aren't making these advances alone. We leverage intergovernmental expertise, we collaborate with academics, and we utilize, when possible, commercial imagery contracts that support civil applications. The Satellite Analysis Branch is based in the Washington, D.C. metro area. It operates on a 24/7 basis with a team of approximately 20 analysts. It has 5 long-standing operational desks that disseminate rapid response, value-added products needed to support federal and state governments, local authorities, disaster management agencies, and civil protection authorities. We have an analyst staffing each one of these 5 product areas, and their responsibility is to inspect and interrogate the satellite data and transform it into usable information needed to support decision making. Our product areas include fire and smoke mapping, marine pollution detection and monitoring, both oil spills and marine debris, volcanic ash detection and forecasting, heavy precipitation guidance, and tropical cyclone position and intensity estimates. For two of these product areas, we employ the NV Analytics software to do our hazard mapping, and those are the product areas of fire and smoke and marine pollution. So currently in the US, there is a lot happening in the weather and the environmental world. There are record-breaking wildfires that are raging in the West. Hurricane Laura is set to make landfall along the Gulf Coast later today as a major hurricane. Tropical Depression 13 is swirling off the northwest coast of Mexico, and Reventador and Sangay volcanoes are erupting in Ecuador. And each one of these hazards falls within the mission responsibility of the NOAA Satellite Analysis Branch. And so the monitoring show must go on, despite that we're a geographical hotspot in a global pandemic. So we flex, we adapt, and we creatively solve to continue to meet the needs of the mission. So currently, the Satellite Analysis Branch is somewhat in an evolutionary phase. We are in the process of advancing from only being involved in large-scale weather watch operations to being able to detect and map small-scale hazards like marine plastics. And although they're individually small, they collectively pose a major environmental threat. So we'll get to more on that topic in just a minute. So to make sure that everyone in the audience is awake today, it is time for a pop quiz. Surprise! Because after all, this is an analytics symposium, and I quite enjoy audience engagement. So in this very simple exercise, I'll demonstrate how a question about one satellite data set can be answered with another satellite data set to emphasize the importance of merging different sources of information into one single improved assessment. So please take 10 seconds to channel your inner student and determine whether you believe that the white cluster of pixels towards the bottom left portion of the image is A, an island, B, a vessel, or C, a cloud. Your hint is that the sensor is NASA MODIS, 250 meter pixel resolution, and the image location is in US waters. The answer will be revealed at the end of the keynote, so make sure to stay with me. Okay, shifting gears into a real-world analytical application. Here is one component of what geospatial vision in the next decade looks like at NOAA. So aligning with the theme of the symposium, I had to first acknowledge that in order to know where you're going, you have to reflect on where you've been and what you've learned. So, in the context of addressing marine debris, I'm going to first take us back nearly 1 decade ago to March 2011 off the coast of Japan, when a devastating 9.0 magnitude earthquake struck and subsequently triggered a massive tsunami. You can see from this high-resolution optical image in panchromatic form that the structures have just been decimated by the inundation of water. So it was immediately obvious of the scale of the impacts of this event. It ultimately claimed well over 10,000 lives and created a nuclear disaster. NOAA's Ocean Service cites that the government of Japan estimates that more than 5 tons of debris was swept into the ocean by this wave. And towards the bottom portion of the scene, you can see just how inundated and underwater portions of the port are at this time. So estimates vary on how much of this debris sank versus how much began to be transported east across the Pacific Ocean. But over time, large pieces of individual debris, such as docks and airtight shipping containers, they began to wash ashore in Hawaii, in the Aleutian Islands, and in the Pacific Northwest. And so there was alarm at the highest levels of the US government of the possibility of large rafts of potentially radioactive debris about to imminently affect US shorelines. So NOAA, being a federal science agency, was tasked to investigate this concern. And so we in the NOAA Satellite Analysis Branch, we set out on an ambitious special effort to attempt to confirm or disprove this concern. So we worked closely with the then Excelis company, which today is L3Harris, to use the ENVI software and its functionality to visually inspect high-resolution imagery that was acquired off the coast of Japan, and then spectrally interrogate the features in the scene. So looking at the larger image in the background, the debris rafts are very obvious. There's a landmass that with green vegetation, and then the whitish colors due to the enhancement. Those are the areas of debris that was washed out to sea. But we had to come up with a creative way to map this in a time-sensitive manner such that the information was still actionable. And then we also needed a way to verify that the features we were analyzing were in fact composed of debris. So in this process, we created N members. Each one of these colored spectral curves on the right, they represent a predominant pixel composition within the scene that is very unique compared to water. So we saved these spectral curves as a library and used them to run a target detection. And so what we found is that of one of those N-member spectral curves, one of them represented the debris rafts strikingly well. And so right now I'm showing a zoomed in version of some of those larger areas of debris. This is within 1 to 3 days after the tsunami. And then taking the spectral curve number 3 and having the computer ENVI's functionality delineate the extent for us. And though the red outline is slightly tilted, you can see how well it actually matches the rafts in the scene. So we used that specific curve, and then we applied the technique to a larger portion of the image and discovered that we had the ability to produce a rapid assessment of marine debris in a semi-automated fashion. But that's too easy, right? Science always seems to have a way of cutting us down to size and keeping us humble. And unfortunately, this technique, this procedure, it didn't translate to imagery out in the open ocean. And that's for several reasons. At some point in time, these debris rafts dismantled, they became weathered, composition potentially changed, plastics became increasingly smaller due to photo degradation. So looking back on this event in approximately 1 decade ago, if I had a redo, I would have gone to great lengths to repeatedly image these debris rafts day after day to understand if we could have continually built that spectral library as it evolved and just continued to monitor the state of this debris. So the lesson learned is that the conditions off the coast of Japan immediately after the tsunami didn't translate to our open ocean analysis, which we ultimately struggled with on and off for several years. So that brings us to the present. Be cognizant of where you are now and what challenges currently exist in your realm of expertise. So for us, that challenge is that debris events aren't limited to natural disasters, and that humans play a significant role in the marine debris crisis. It could stem from improperly discarded waste, overuse of single-use plastics, and another potential source is derelict fishing gear. All of these pose a serious threat to marine life, the environment, navigation safety, the economy, and human health. And the scope of this threat is not fully comprehended. But what we learned from the Japanese tsunami and then our subsequent endeavor to characterize marine debris out in the open ocean, it doesn't stop just because the threat from the natural disaster in Japan ultimately subsided. We still have several sources of marine debris and marine plastics that need to be understood on a broad scale. So the question is, can ocean plastics be detected with satellite? Here's a diagram of the garbage patch, and it's a region that's largely data void of very high resolution acquisitions. And within this gyre and throughout the Pacific, there are macroplastics in the form of the aforementioned derelict nets. They're also commonly referred to as ghost nets. And the photo credit here goes to Ocean Voyages Institute, who posted these pics online, and they're from their latest cleanup mission. So I wanted to show an actual photo of these ghost nets to provide a sense of size and the impacts they have to marine life, as you can see in the left. These nets are massive and often take cranes to lift them out of the ocean, and they could weigh several tons. So the focus now shifted from the natural disaster in Japan to attempting to identify macroplastics debris targets in the open ocean. So about 3.5 years after the tsunami, we came across a project of opportunity to work with other line offices in NOAA that were conducting a large-scale debris cleanup mission at an atoll in the remote northwest Hawaiian Islands. And there was a particular net that they were aware of, and they provided the coordinates to us for. And we internally refer to this net as Casper. And this net was snagged on a coral reef. It was stationary, and it offered us ample time to task high-resolution imagery before it was ultimately dismantled and removed. So in the imagery, on initial assessment, I first noticed that in the multispectral true color RGB composite shown on the left, you'll probably have to direct your attention to the zoom box below. That pixel in the center is the location of the net, and I noticed it had a little bit of color information. There was an orangish tinge to it, but not much shape. And when viewing the panchromatic pair, which is shown on the right in black and white, I noticed that the net exhibited a curved shape. So later in the mission, we had an in situ photo that was provided to us that actually confirmed both of these characteristics for color and for shape. And it provided us one of our first pieces of open ocean ground validation. And we were able to start learning about the way these nets present in high resolution optical imagery and how they emit in the electro-optical spectrum. And so our spectral library continued to grow. So here I will reference a publication that came out just a few months back out of Plymouth Marine Laboratory in the UK, titled Finding Plastic Patches in Coastal Waters Using Optical Data by lead author Lauren Bierman et al. So in this case, the sensor is Sentinel-2. So different from what we used in the projects I just described. And though the band wavelength combinations of these sensors were not identical, they were close enough for us to assess similarities in the trend. And so what we were able to learn from the Japanese tsunami and learn from the ghost net in the Northwest Hawaiian Atoll, and then comparing with this paper, is that with marine plastics, we most typically see a downward trend in the blue portion of the spectrum and a distinct peak in the low to mid 800 nanometer range, most often centered around 840 nanometers. And so we take this knowledge and we continue to move forward to see if we can identify any potential net targets without having any kind of ground truth or ground verification. So here I am showing you how two separate pixels look visually. They're within the same scene, same part of the ocean, and they both stand out from their surroundings. They're a little more distinctive in the color features. So I want to use this to emphasize that how spectral information becomes crucial when visual inspection only does not suffice. So with the exception of a little bit of a color disparity, there's not much difference between these two pixels until we look at their curves. So the one on the left exhibits the downward trend in the peak after 800 nanometers, whereas the pixel on the right exhibits the quintessential curve of water. So this quickly leads to the conclusion that one of these pixels warrants further investigation, and one is nothing more than part of the ocean background, perhaps a whitecap. So what does this mean for our vision in the next decade for marine debris at NOAA? And simply put, it means we have a lot of work to do. There was a years-long gap in some of the studies I presented, but now in 2020, we believe that the satellites are advanced enough, the technology is sophisticated enough, and that we know people who have the right expertise to help pioneer the standard of using remote sensing to map open ocean marine plastics. So our latest breaking news is that we've made encouraging strides in using NV workflows to detect macroplastics. So here, in a short summary, we're applying a noise reduction transform and parsing out pure pixels and reviewing which of these pure pixels are the most spectrally unique in an n-dimensional space. And the preliminary results are exciting. These results are from mid-2020. And some results are so new that I was not even able to include them in the talk this morning. And so the goal for us, hopefully in the first half of the decade, is to find more imagery sources, that have different spatial resolutions, different spectral ranges that could potentially collect concurrently, so that it's possible to piece them together to create a blanket map over a large swath of the ocean. The intent is to scientifically report on the scale of the marine debris crises in the open ocean, direct future ocean cleanup missions, and promote awareness that this is a huge problem. And perhaps this message can potentially do a small part to motivate change. So my advice in closing statements is to rise to the challenge, intentionally and mindfully. I had a stage here today, but I challenge you all in the audience to identify one vision that your agency, your company intends to fulfill in the next 10 years and go all in. Collaborate with your peers and external experts to the maximum extent possible. Although I understand this advice could much more apply to the public sector rather than the private. gain a new perspective. So it's not often that I'm outside of my own operational bubble. And so I'll quickly share with you one point that was made yesterday during the morning panel that I found to be enlightening. So I will share my perspective here. And that is, it was said that the need, or perhaps desire, I apologize if I misstate, for government to buy commercial data at scale in order to make the commercial company sustainable. So saying there was some kind of need for governments to make these purchases at scale in order to make those companies sustainable. And I really listened to that viewpoint, and it makes a lot of sense. And I put a lot of thought in how that relates to my own work. So being on the side of the civilian side of a government agency, NOAA, that already operates its own fleet of geostationary and polar orbiting sensors, we receive a relatively tiny amount of commercial data. But as you've seen in the slides, we rely on it for our emerging areas of hazards mapping. So I see this as somewhat of a chicken and the egg problem. In my office, it can be overwhelmingly difficult to secure adequate funding for commercial imagery budgets. But without having the necessary access to new imagery sources, it's difficult to clearly demonstrate the proof of concept to advocate for said budget. So we make do with our small funding allowance that we have access through our Civil Applications Committee. Find a new data point. For me, it's been learning all about the amazing new and upcoming satellite constellations, and I am immensely impressed. And lastly, talk about your mission, tell your professional story at each opportunity, and make a connection. I look forward to chatting with some of you this afternoon. I'll be present in the virtual rooms later today. And without further ado, the answer to the pop quiz: what is a vessel? So the image on the right is Sentinel-2 10-meter optical data collected at approximately the same time the MODIS sensor was overhead, and simply due to spatial resolution, we can make a much better assessment of what that structure is, and more importantly, that it has possible pollution anomaly associated with it. So this was relevant to our operations in the satellite analysis branch. So if you answered B, give yourself a high five. And once again, I'm very grateful to L3 Harris for the opportunity to open day 2 of the EAS. To the symposium organizers, thank you so much for making this easy to participate in. To my NOAA colleagues, and last but not least, my sincere thanks to you in the audience for your time and attention. Thank you.